Welcome, everyone, to today's Explainer. If you're an IT professional diagnosing hardware, whether you're out in the field or sitting right at the bench, you absolutely know that having a rock-solid mental model of a computer's architecture is, well, it's everything. So today, we're breaking down the anatomy of a system. Think of this as your foundational masterclass. We're going to pull apart the subsystems, look at exactly how they communicate, and trace the whole journey of data, right? From the moment a user clicks a button all the way to the final printed page or saved file. It's going to be a fantastic refresher, and it's definitely going to sharpen up your troubleshooting skills. Okay, let's dive into this. Here is our roadmap for the session. We'll start with the hardware big picture, move into memory and the CPU, check out input technologies, explore output devices, and wrap up with secondary storage. Compartmentalizing these 5 categories is literally how you build a reliable mental model for field troubleshooting. All right, part 1, the hardware big picture, looking at the broad categories. Before we get totally lost in the weeds of specific components, we always have to remember that every single piece of hardware falls neatly into one of 3 broad subsystems. And this brilliantly illustrates the input, process, output, or IPO cycle. This is the fundamental heartbeat of computer hardware. Data flows in from input devices on the left, like your keyboard or your mouse. Then it travels into the central processing unit right in the middle to be processed. And finally, the results flow out to the output devices on the right, like your monitor or printer. So whenever you're diagnosing a tricky system failure, your very first question should always be, where exactly in this cycle is the breakdown happening? Moving right along to section 2, memory and the CPU, our processing center. So this is where the central part of that IPO cycle actually happens, the absolute brain of the computer. Now, for the CPU and main memory to actually work together, they rely on 3 interconnected groups of connections called buses. Honestly, it's best to think of these like a city's infrastructure right on the motherboard. The data bus, that's your highway, physically transferring the input and output data back and forth. The address bus is your GPS system. It locates the exact unique storage locations, or addresses, within the memory so the data knows exactly where it's going. And finally, the control bus acts as the traffic lights, sending out the read or write signals that control the whole operation. If any of these buses fail, well, the CPU simply cannot communicate with the memory. End of story. Now, intimately connected to the system's brain is ROM, or read-only memory. This is where the permanent programs live. And you know what's incredibly fascinating from a manufacturing standpoint? If you look at a completely unprogrammed PROM chip, its data is made up entirely of ones. It's literally just a wall of ones. It isn't until a special device programmer comes along and applies a direct electrical charge to the input pins that the data is actually written into it. Over time, ROM technology has evolved dramatically, mostly to solve the huge headache of updating permanent data. First, we just had PROM, which is strictly one-time programmable. If you make a mistake, you literally throw the chip in the trash. Not great. Then came EPROM, which is amazing. It actually has a tiny physical window on top of the chip. You expose the silicon to a strong ultraviolet light to erase the data and reset it. Wild, right? Following that, we got EEPROM, which thankfully ditched the UV light in favor of electrical reprogramming, but you still had to pull the chip out and put it in a special machine. Finally, we arrived at Flash ROM, which can be reprogrammed right there inside the computer. It's incredibly fast, with access times hovering around 45 to 90 nanoseconds, and it's what we all use today to easily upgrade firmware and devices like modems. All right, on to section 3, input technologies, or how the computer senses the world. This is how the computer senses the outside world, converting physical human actions into digital data. Let's move to and see how this builds from legacy to modern input methods. On the left, we have the gold standard, the mechanical 104-key QWERTY keyboard. As an IT pro, you know these require strict physical cleaning best practices. We're talking regular blasts of compressed air and careful wipe downs with isopropyl alcohol to maintain that keystroke reliability. But check out the right side. This is a virtual keyboard. It's essentially a software device acting as a hardware interface, projected and controlled by an application or a touchscreen. It's the exact same input function, but an entirely different underlying technology for us to troubleshoot. We see a very similar leap when we look at pointing devices. Just think about the old mechanical mouse compared to a modern optical mouse. The mechanical version completely relies on physical contact. You have a small rubber ball rolling against 2 internal rollers as it drags across a mouse pad. The optical mouse, on the other hand, is vastly more accurate and has exactly 0 moving parts, using a precise laser to detect surface movement. It's a total game changer for reliability. Now, what's really interesting about this slide is getting a literal look under the hood of that legacy mechanical input. It reveals immense physical complexity. As IT techs, sure, we don't see these every day anymore, but just look at that tracking ball, the rollers, the analog sensors. If a user reported a jittery cursor back in the day, it required dedicated, routine physical maintenance. You're opening the chassis, removing the tracking ball, and using a swab with cleaning solution to literally scrape the accumulated gunk off those little analog rollers. It was very hands-on. But input devices go way beyond standard keyboards and mice, especially in enterprise environments where you need massive data entry automation. OMR, or optical mark readers, scan special pre-printed forms and convert dark pencil marks into electrical pulses. This is exactly how massive stacks of multiple choice exams get graded in seconds. Then you have OCR, optical character recognition, which scans printed text and intelligently turns it into editable word processor documents. And of course, MICR, magnetic ink character recognition. This reads actual magnetically charged ink shapes and is heavily used by banks to process checks securely. These enterprise imports are all about eliminating manual human error and processing data at scale. However, and this is a big however, this heavily relies on strict routine maintenance. IT teams absolutely must continuously clean the glass platens of OMR and OCR scanners and constantly run software calibrations. If you don't, you risk devastating automated data entry errors across the whole system. Let's pivot to Section 4, output devices, which act as the computer's voice. If input is the computer's senses, output is its voice. This is where processed data is finally transformed into soft copy or hard copy. For soft copy, we rely on monitors. Just look at this incredible progression from the massive, heavy CRT monitors of the past to modern, sleek LCD and LED flat panels. All monitors produce images built from thousands or millions of tiny dots called pixels. The resolution determines the quality, and we've scaled all the way from legacy 640 by 480 pixel resolutions up to the massive crystal clear HD densities that we support today. Now, when we actually need hard copy output, we turn to printers. This hierarchy tree is a phenomenal tool for troubleshooting in the field. Notice how it immediately splits all printers into two distinct families: impact printers and non-impact printers. Knowing which branch of this tree your hardware falls under dictates your entire maintenance and troubleshooting approach. The difference between these two is striking. Literally, impact printers, like your line printers or dot matrix models, work by physically striking a metal pin against an inked ribbon directly onto the paper. They are noisy, they are mechanical, and they are relatively slow. But they are incredibly robust and uniquely capable of printing through multiple layers of paper for bulk carbon copy forms. Non-impact printers? They don't use a physical striking device at all. Instead, the flow of ink is meticulously controlled by an internal processor. They are remarkably quiet, highly precise, and much, much faster. Looking deeper at non-impact output, the technology varies wildly based on exactly what you need it to do. Thermal printers use electrically heated pins on special heat-sensitive paper. They are cheap, low maintenance, and great for fax machines or retail receipts. But their fatal flaw? That thermal paper darkens and fades over time, especially if you leave it in sunlight. Laser printers, meanwhile, use a precise laser beam and dry powder ink to process an entire page all at once, delivering massive graphics quality ranging from 300 to 1200 dots per inch. And then we have plotters. Rather than printing a matrix of closely spaced dots, plotters use a mechanized arm holding actual colored pens to draw flawless, continuous lines. This makes them the absolute gold standard for complex engineering and architectural blueprints. Finally, Section 5, secondary storage, where we keep permanent data. We've traced the data all the way through the IPO cycle. But what actually happens when the power is finally turned off? Well, it survives here, in secondary storage. This is an exposed hard disk drive, and honestly, it is a masterpiece of physical mechanics. What you're looking at is a platter covered in metal oxide, spinning at an absolutely incredible 7,200 revolutions per minute. That tiny electromagnetic read-write head on the arm interacts with the platter to perform operations. And the data isn't just thrown on there randomly. No, it is highly meticulously organized into concentric circles called tracks, divided into sectors, and aligned perfectly across multiple platters into cylinders. So the crucial point is understanding the divide between magnetic storage and optical storage. Magnetic storage, like that hard drive we just saw or those old portable 3.5-inch floppy disks, uses metal oxide to store data. Though, to put things in perspective, a floppy maxed out at just 1.44 megabytes. Optical storage, on the other hand, changed the game entirely. A CD-ROM holds a massive 682 megabytes. It spins a highly reflective disk, while a near-infrared laser beam reads microscopic dark spots called pits and lighter areas called lands. Think about that. It's literally reading data with light. It's incredible. And that brings us right to the end of our masterclass. We've seen how hardware has evolved from mechanical mouse rollers and UV-erased ROM chips to virtual laser keyboards and near-infrared optical storage. It really begs a fascinating question for those of us in IT support. As input technology entirely sheds mechanical devices in favor of virtual lasers and software interfaces, how will the fundamental input-process-output cycle evolve next? It's definitely something to think about the next time you're diagnosing a cutting-edge piece of hardware. Thanks so much for joining me on this explainer, and I'll catch you in the next one.